Hello, everybody. In today's lesson, we're going to be starting lesson 7.1 ratios, rates, tables, and graphs. We're in the sixth grade Go Math textbook for middle school, and we're on page 173. So let's go ahead and get started. So in the Explore activity, we're going to be finding ratios from tables. So students in Mr. Webster's science classes are doing an experiment that requires 250 milliliters of distilled water for every 5 milliliters of ammonia. The table shows the amount of distilled water needed for various amounts of ammonia. So if I have 2 milliliters of ammonia, I need twice as much distilled water. 50 times as much distilled water, so 2 times 50. And we can confirm that by looking over at the very end. We have 5 milliliters of ammonia, and we need 50 times that amount of distilled water. So basically, it's going to be 3 times 50. So if you tell me the amount of ammonia, I just need to multiply by 50 to find out how much distilled water I need. So 3.5 times 50 is 175. And then what number times 50 is 200? Well, that's 4, right? 4 times 50. All right. So we've completed the table. Now use the numbers in the first column of the table to write a ratio of distilled water to ammonia. Distilled water to ammonia. So we have 100 milliliters of distilled water compared to 2 milliliters of ammonia. Okay. How much distilled water is used for 1 milliliter of ammonia? So if I have 1 milliliter of ammonia, we can do this. Divide by 2 to get a 1 milliliter of ammonia. And we'd have 50 milliliters of distilled water. So if we reduce this to just 1, so for every 1 milliliter of ammonia, you're going to need 50 milliliters of distilled water. All right, so now use your answer to write another ratio of distilled water to ammonia. Well, that's simply 50 to 1, right? Instead of 100 to 2, we can say 50 to 1. All right, look at C. The ratios in A and B are equivalent or not equivalent? A and B. Well, the only difference between A and B is that I reduced B by dividing both of the numerator and denominator by 2. So they are equivalent. All right, D. How can you use your answer to B to find the amount of distilled water to add to a given amount of ammonia? Okay, we've already talked about this. Simply multiply the amount of ammonia by 50. All right, how about E? So 100 to 2. If we have 3 milliliters of ammonia, we're going to have 150 milliliters. Okay, so basically we're using this table up here. If we have 3.5 milliliters of ammonia, we're going to have 175 milliliters of distilled water. If I have 200 milliliters of distilled water, that will be 4 milliliters of ammonia. And the final one, 250 milliliters of distilled water will be 5 milliliters of ammonia. All right, so let's reflect. Let's look at this pattern, or look for a pattern. For every 1 milliliter of ammonia, there are blank milliliters of distilled water. There's 50. 50 milliliters of distilled water. So for 6 milliliters of ammonia, well, that would just be 6 times 50. So that would be 300 milliliters of distilled water. Okay, simple as that. All right, so let's look at page 174. All right, now we can also graph with the ratios. And so we're going to copy the table from Explore Activity 1. All right, and so now these are technically coordinates on a graph. So we have 2 and 100, 3 and 150, 3.5, 175, 4, 200, and 5, 250. So graph the order pairs. Because fractions and decimals can represent amounts of chemicals, we're going to connect the points because we're going to have half a liter. All right, so 2 and 100. And they've already got 5 and 250 for us. So 3 and 150. 3.5 and 175. 4 and 200. Okay, and now we're going to just connect the points. Okay, so what do we have? We have a straight line. If we were describing the graph, we would say we have a line. All right, for C. For each ordered pair that you graph, write the ratio of the y coordinate to the x coordinate. Well, for every y or x that we graphed, the y increased by 50. So we simply write 100 over 2, 150 over 3, 175 over 3.5, 200 to 4, and 250 to 5. Okay, where the numerator is the y coordinate and the denominator is the x coordinate. Okay, so the ratio of y to x. All right, so the ratio of distilled water to ammonia is blank over 1. It's 50 to 1, right? And how are the ratios in C related to this ratio? Well, these are all multiples of 50 to 1. They're equivalent. So, and how about E? The point 2.5, 125, is on the graph, but not in the table. The ratio of the y coordinate to the x coordinate is what? And how is this ratio related to the ratios in C and D? Okay, well, the y coordinate is 125, and the x coordinate is 2.5. Well, if we multiply 2.5 by 50, we get 125. 50 times 2 is 100. Half of 50 is 25, so 125. So how is the ratio, this ratio, compared to the ratios in C and D? They're equivalent. If it's on the line, they're equivalent. So for 2.5 milliliters of ammonia requires 125 milliliters of distilled water. What do you think is true for every point on the graph? Well, the y coordinate Okay, so for every y coordinate on the line, so the y coordinate gives the amount of the distilled water needed for each amount of ammonia given. So 2 milliliters of ammonia, 100 milliliters of distilled water, and so on. So number 2, how can you use the graph to find the amount of distilled water to use for 4.5 milliliters of ammonia? Well, we would simply look for 4.5. Okay, so in the middle of here is 5, 4, 5, 6. So 4.5 would be in between 4 and 5, and then we would see where the corresponding y coordinate is. So find the x coordinate. So once you find 4.5 on the graph, the y coordinate is going to tell you how much distilled water you're going to need. All right, so let's look at 175. Okay, so we can also represent rates with tables and graphs. So let's look at example 1. All right, an express train travels from Webster to Washington, D.C. at a constant speed. Constant speed means it's the same speed throughout the trip. And it makes the trip in 2 hours. All right, so it's 120 miles between these two. So we can write a ratio of distance to time to find the rate. So distance over time, the distance was 120 miles. The time was 2 hours. So if we reduce that by a factor of 2, we get 60 miles per hour. So the unit rate is 60 miles per hour. So the unit rate, 1 hour, 60 miles. 2 hours, 120 miles. 3 hours, 180 miles, and so on. So then we can graph the information from the table, writing the order pairs 1 and 60, 2 and 120, 3 and 180, 4 and 240, 5 and 300. And we notice that we can have a fraction of an hour, right? And we can also have half a mile. So we can connect these points on the number line. On the graph. So we're going to graph the order pairs. Fractions and decimals can represent times and distances, so connect the points. And use the graph to find how long the train takes to travel 90 miles. So we'd find 90 miles on our graph, which is going to be in between 60 and 120. And so we'd go across, and we see that it's about 1.5 hours. It's in between 1 and 2. Okay. And so that's what they're saying in C. The point 1.5, 90 is on the graph, so the train takes 1.5 hours. Okay, so now you try. Let's look at number 3. So a shower uses 12 gallons of water in 3 minutes. Complete the graph and table. Suppose the shower used 32 gallons of water. How long did it take? How long did the shower take if we used 32 gallons of water? We have a rate or ratio of 12 gallons for every 3 minutes. So we can find a unit rate for gallons per minute. So 12 gallons in 3 minutes. All right. Well, 3 times what is 12? 3 times 4. So we're going to use 4 gallons of water for every 3 minutes. So we can write this like this. Divide numerator and denominator by 3. And we get 4 to 1. 4 gallons every minute. So in 2 minutes, it would be 8 gallons. 3 minutes, 12 gallons. 4 minutes, 16 gallons. 20 divided by 4 would be 5. And 6 times 4 is 24. But they said, what if we take 32 gallons? Well, let's go ahead and graph 2 and 8, 3 and 12, 4 and 16, 5 and 20, 6 and 24. Okay. So can we have a fraction of a gallon of water? Sure. Can we have a fraction of a minute? Sure. So let's connect the points. All right. And it said 32 gallons. How long would it take? Okay. Well, 32 gallons. The x coordinate for that is 8 minutes. Okay. Is that reasonable? Yes, because 8 times 4 is 32. Okay, so it's going to take 8 minutes. All right, let's look at page 176. All right. So let's finish up our first part by doing the guided practice, numbers 1 through 6. All right. The ratio of oxygen atoms to sulfur atoms in sulfur dioxide is always the same. The table shows the number of atoms in different quantities of sulfur dioxide. And complete the table. So sulfur to oxygen, 6 sulfur atoms, we need 12 oxygen atoms. So if we're just looking at that, if we had divide that by 6, we would see that for every 1 sulfur atom, we need 2 oxygen atoms. So just multiply sulfur by 2. So we need 18 oxygen atoms for 9 sulfur. 21 times 2 is 42. And half of 54 is 27. So what are the equivalent ratios shown in the table? We can say 12 to 6 is equal to 18 to 9, which is equal to 42 to 21, which is equal to 54 to 27. All right, number 3. Stickers are made with the same ratio, length to width. All right. A sticker 2 inches wide has a length of 4 inches. So 2 inches wide to 4 inches long. All right. So 2 to 4, we can simplify that by dividing by 2. So we get for every 1 inch in width, we need 2 inches in length. So basically, same as the sulfur atoms and oxygen atoms, we're going to multiply the width by 2. So 4 times 2, 8. 7 times 2, 14. Half of 16 is 8. So what are the equivalent ratios shown in the table? Well, 4 to 2, 8 to 4, 14 to 7, 16 to 8. Okay, number 5. So 5 boxes of candles contain a total of 60 candles. Each box holds the same number of candles. Compare the table and the graph. Complete the table and the graph. Suppose you have 84 candles. How many boxes is that? All right, so we have 60 candles. And we have 5 boxes. Well, 5 is a common factor, so 1 to 12. So every box has 12 candles. So 8 times 12, 96. 120 divided by 12 is 10. Okay, so let's go ahead and graph this. 5 boxes, 60 candles. Eight boxes, 96. 10 boxes, 120. Okay, now on this one, we're not going to connect the points. Because why would you put half a candle in a box? Or why would you have half of a box? Okay, so we're not going to connect those points. All right, so the question then on number 5 is, suppose we have 84 candles. How many boxes is that? Well, remember, it's 1 to 12. So 84 candles divided by 12 will tell me the number of boxes. Well, 7 times 2 is 14. Carry the 1. 7 times 1 is 7, plus the regrouped 10. So 7 boxes. And we can put that right there on the number line, or on the graph. 7 and 84. All right, number 6. How do you represent real-world problems involving ratios or rates visually? Well, we would make a table of several equivalent ratios. Or rates for the quantities. Okay, so make a table of several equivalent ratios or rates for the quantities, and then we're going to use the table to make and graph ordered pairs. And then, if appropriate, connect the points. Okay, so let's look at that again. How do you represent real world problems involving ratios or rates visually? So we make a table of several equivalent ratios. We use the table to make and graph the ordered pairs, and if appropriate, we connect the points. Okay. Now, I notice I skipped number 4, so let's go back and look at number 4. Graph the relationship between the width and the length of the stickers in exercise 3. So we have a width of 2, and we have a length of 4. We have a width of 4 and a length of 8. We have a width of 7 and a length of 14. We have a width of 8 and a length of 16. Now, can we have half of a inch? Sure. So we can connect the points. All right, so we're going to, that's it for part 1 of this lesson. So in the next video, we'll talk about the independent practice for this lesson.